Hello, my name's Brian. I'm an agile management consultant, and earlier last year I left the smoke of old London town and headed north. Welcome to glorious Yorkshire. Now I'm using the agile management practices to get stuff done around the house. We have some grand plans on the roadmap. But plans are nothing. We've actually got to get stuff done. But if agility is just a bunch of silly words to you, then don't worry. Stick around. Just enjoy watching stuff getting done. Every story has a beginning, a middle, and an end. These 4-inch square oak beams, they are not the beginning. Fabricating them may be the middle. Construction may be the end. But the beginning is elsewhere. It all begins with an idea. For the gardener that needs secure covered storage for their expensive lawn tractor, the lean-to is a structure against the side of the garage which provides secure covered storage for lawn tractor, wheelie bins and much more. Unlike being stored outside exposed, this protects the lawn tractor from the elements and preserves its lifespan. Much as I would love to start construction immediately, first I need to fabricate the structure that is going to be built. Before I start fabricating, I need the designs for what I am going to fabricate. And before I can design anything, I need to understand the context and requirements. This presents an opportunity for illustrating how work breaks down, how you get from the big problem of providing covered storage for the lawn tractor to little problems that can be solved. We've already seen the first level of refinement. Requirements, design, fabrication, construction. There will be feedback, there will be overlap between those areas, but essentially it is a linear progression. Before you can start construction, you need to fabricate the pieces you're putting together. Before you can begin the fabrication, you need the designs for what you're fabricating. And before you can begin the design, you need to understand the context and the requirements. The context of where it's going to be is right here, against the garage. This is where the lean-to will be. So my primary requirements are: what is the size of the space that the lean-to is going to fit into? The first requirement is covered storage of the lawn tractor. The size of the lawn tractor can be found in the manufacturer's specifications. Whilst I can easily get the dimensions of the lawn tractor from the technical specification, what that doesn't tell me is what height do I need when I'm sat on the lawn tractor. For that, I'm going to have to break out the tape measure. Roughly there. Call it that brick. 67 inches, 170 centimetres. Oh, whilst I'm here, what height am I? Shorter. That'll be okay. 87 inches, 221 centimetres. This is the key dimension. The lean-to has to fit beneath the roof soffits here. If it goes any higher, then it's changing the structure of the roof, and the cost of changing the roof is going to go through the roof. Will everything fit? The next step is to determine the cross-section of the lean-to, and for that I need to fix a few more variables: width, slope and roof thickness.
There is a minimum width, the width of the lawn tractor, but I also need space around it in order to climb on and off of it. I want to use paving stones as the floor of the lean-to. They are 400mm square, so the width is going to be a multiple of 400. The lawn tractor is just over 1000mm in width, and the wall of the lean-to is likely to be 100mm. So 1200mm feels a little too tight. 1600mm feels like the optimum. I will use that for the remaining experiments. Some quick experiments, mock-ups to understand how thick different roof structures might be. The various components just stacked up to determine a thickness. This doesn't need absolute precision. A few millimeters either way isn't going to influence the decisions about which structure to use. Tiled roof has a thickness of around 120mm. I don't have any roofing felt to add to the mock-up, but its thickness is minimal compared to the rafters, so it can be ignored for now. A plywood and roofing felt on battens has a thickness of around 110mm. All of that data can now be put into a simulation of the roof. The two variables that can be played with are the roof slope and the lean-to width. Success is the roof height at the midpoint of the lean-to is higher than the height of a person sat on the lawn tractor. Not every possibility meets the success criteria. The 30-degree slope needed for normal roof tiles simply isn't going to work. Even a 10-degree slope is touch and go. If the thickness of the roof can be reduced, then that gains more height on the inside. Turning the rafters sideways gains 20 to 25mm. This wouldn't conform to building regulations if this were the roof of a domestic dwelling, but this is an outbuilding. The distance is short, and the number of rafters will be enough that it will work. If it were a domestic dwelling, then I would need to sit down and do load calculations. Removing the battens gains me even more. The rafters will be sufficiently close together that the plywood can support the weight. This is half the thickness of the roof. This may not sound like much, but it could be the difference between clashing my head on the roof or driving out smoothly. Next, I need to think about the structure that will form that shape. There are options here as well.
I could brick build the lean-to. It would require larger, more substantial foundations, and whilst I have done bricklaying before, here on the pizza oven, that was me, to do an entire wall, I probably want to engage a professional bricklayer. More cost again. I could use simple timber construction, little more than a shed leant against the garage wall. Studs and battens supporting an external weatherproof skin, very similar to the stud wall here in the garage workshop. Not too costly, fairly easy to build, but will it stand up to the Yorkshire weather? Will I be rebuilding it again after just a few years? Timber framing, a self-supporting structure held together with properly cut joints. More costly than simple timber work, but more structurally sound. I can do timber framing. I have built timber-framed buildings before. As much as this is an economical decision, the costs involved, it is also an emotional decision. I want to build something. I'm a creative person. I like creating things. To have somebody else do that for me, well, that just depresses me. For me, the journey to get there, the process, is as important as the destination. You already know it's going to be timber framed. We are sitting in front of the oak. but the oak is going to have to wait a little bit longer. There is still more design work to be done before I can start cutting the joints into the posts and rails.
Design. Iterative development. It starts out with a hand-drawn sketch. Mistakes here are easy to correct. It's just paper, whereas cutting timber is costly. Saws, drills, routers, none of them come with an undo button. Once I'm happy with the sketch, the next iteration is to fire up the computer-aided design package to refine the sketch into a structure, and from there to engineering drawings of what to fabricate. I have built timber frame buildings before, so I'm familiar with the basic joints and structures. I'm constantly trying to think ahead. Thinking ahead avoids silly mistakes that could impact the later stages. I need a design that I can fabricate, and then I need to be able to assemble it. You're watching this sped up by a factor of 6, so that my long pauses to stop and think go by in a flash, rather than the 30-40 seconds of silent contemplation. The challenge with thinking is that the progress isn't immediately visible, whilst thoughts are still rattling around inside the head. I approach the design in a very similar way to how I will fabricate it. I start with a block of timber, and then every other operation is removing material through carving or drilling. I try to always start from one of the original faces and to use the original edges as reference. This means the order of operations is important. The mortise needs to be formed on the flat surface before the shoulder destroys the flat surface. These become the instructions to myself for fabrication. The top of the post is a shouldered tenon joint. The shoulder takes the weight of the beam, the tenon secures it. I intend to route as much of the joint as possible. There will inevitably be hand finishing, mostly squaring the rounded corners that the router produces. There are a few places where the rounding doesn't need to be squared off and can be incorporated into the design. The inner edge of the shoulder notch on the post is one of these places. To complete the post design, I need to know where the brace mortises are located, which means I need to design the braces between the posts and beams. Whilst the brace is at 45 degrees, the tenons need to be perpendicular to the post or beam that they are going into. There are construction challenges to think about whilst designing. The sequence of assembly is important. Beams slide horizontally into posts. Therefore, I can't assemble the brace onto the post and drop the beam onto it because dropping is not sliding, whereas the brace slides into the post. Therefore, I need to assemble the brace onto the beam and slide both of them into the post. I could use a simple straight brace, but that isn't aesthetically pleasing. Adding a slight curve to the underside of the brace makes it feel more natural. This is where computer-aided design comes into its own. I can try different curves quickly and cheaply. I can look at them from different angles. I can experiment with the transitions at the corners, rapidly refining the shape until I have something that I'm happy with. I don't like the slight straight on the corners. The curve gets pushed right to the edge. It doesn't take too long to put together a simple post and beam wall. Then another day of rafters, base beams, studs, tongue and groove cladding, noggins, roof panels, flashing, door casing. The list of parts is unending. Assembling the structure in the CAD package is another opportunity to think about how it will be assembled in real life. Plus, in the CAD package, I can look inside everything and check that all of the designs for the joints are lining up correctly. It's important to get this right now because it's a lot easier to machine the posts and beams in fabrication when they're on a workbench than it is when they're assembled in the final construction. Some quick checks. Is the lowest point on the rafters higher than my height on the lawn tractor? The design is 1759 millimeters, and I said
67 inches, 170 centimetres.
Just over 2 inches, 5 centimetres of clearance, thereby avoiding any roof head interactions. Good to go. Except it's still not time to start cutting timber. Before I commit a blade to the actual pieces of oak, I need to design the tooling that will help me craft the various joints in the timber frame. And I should test that the tooling produces the desired shapes on some scrap timber. I have some spare oak left from the last structure. It's been sat outside for just short of a decade, so it's a little worse for wear, but it'll be fine for use as a test piece. The intent is to use templates machined from spare 12mm ply as the guides for the router. So, back to CAD to draw up the templates. Templates and moulds are always easier said than done. It requires thinking in the inverse, the shape that goes around the shape that you actually want. The templates also incorporate details such as rebates for locating strips that will help with positioning the template on the timber. Again, this is thinking ahead. How is this going to be used in the next stage in fabrication? Once the templates are drawn up, they are transferred into software that converts them into instructions that can be sent to the CNC router so the router can do its stuff. The package that generates the CNC toolpaths helpfully provides a preview window for seeing how the tools will interact with the material being machined. Each template is a few minutes of noise and sawdust as the shapes are carved out. The CNC router creates the templates much quicker and more accurately than I ever could have done by hand.
There we go.
A quick clean-up to remove any excess material where the cutter didn't quite go all the way through. Locating strips are glued into small rebates that were incorporated into the design and which the CNC has machined out. These strips will locate against the timber to position the templates. By getting the CNC to machine them, I know they're accurately positioned, and the small lip gives me something to position the strips against. Of course, the only way to tell whether the templates are going to work is to actually try them out. Better to build a prototype with some scrap than to eat into the actual beams that cost £100 each and have a 2-week delivery time if I mess it up. The timber is never perfectly square nor accurately dimensioned, so careful measurement determines the best faces and edges. The template is butted up against the best edge. The template is designed so that there is additional length to allow clamping without impacting the movement of the router. A template following router bit is stepped down in small increments, just a few millimeters each time, to remove the material. Longer bits are swapped in as it becomes necessary to do so. The template is also used for positioning the holes that will pin the joint together. Whilst working on the prototype joint, I am also taking notes, building up the instructions for how to actually machine the real timbers, determining the order of operations, what to watch out for, where to stop and check measurements. This becomes my playbook for the actual fabrication stage.
Yep.
Although I was trying to minimise it, there is the inevitable bit of hand finishing.
So the answer is, make sure you properly get into the middle, so the amount that we're having to shave off and hand trim is fairly minimal.
All good insight and learning that will be incorporated into the playbook for fabricating the actual posts and beams. Having machined a post, I need to machine the corresponding joint on the end of a beam.
I need to remember to square up the corners with the corner chisel before cutting the shoulder in, because now that we're not a right angle, that corner chisel doesn't work. That's it. That's in. Okay, we're not square yet. Oh, and that. Oh, that is so nice. That's really good. It's decided as the timber is just a little bit more grotty, isn't it? This is not the end, but it is the end of the beginning. We now have a design that we know how to fabricate, and we know the steps to go through to fabricate it. All we need to do now is fabricate the actual frame itself, but that is for next time.